With the growing number of robots in industry and in human environments, the need for ease of deployment and safety in robotics becomes increasingly apparent. Safety can be achieved with stable and collision-free policies, while learning how to perform tasks from a set of demonstrations can reduce the deployment time of robot solutions. Trajectory optimization is a time-consuming process that is not suited for real-time planning. The paths generated also do not generalize to new start and goal positions and are not immune to perturbations on the system. Imitation learning requires demonstrations, which can be tedious to collect. Additionally, the produced policies do not guarantee that the system will be stable or able to avoid collisions with its environment. We propose a novel method for learning stable and collision-free policies. We first use trajectory optimization to automatically collect a set of demonstrations. This set is then used to learn a Lyapunov function through our method. The negative gradient of the learned Lyapunov function is then used as the policy for the robot along with an obstacle avoidance module that we have augmented to deal with convex object pairs. We use neural networks to learn the Lyapunov function, since their gradients with respect to the state input are computable. We use the negative gradient of the learned Lyapunov function, since it guarantees that the Lyapunov stability criteria will be satisfied and provide a stable policy. To verify the performance of our proposed method, we evaluate the method on several different environment scenarios. As a proof of concept, the method was first validated on 2D examples. We start with a hallway environment. We run trajectory optimization on valid initial positions from a grid of sample positions to collect our demonstrations. We see that our method is capable of learning a Lyapunov function for the demonstrations, and the policy rollouts are more accurate to the demonstrations than our baseline. Next, we explore a cross-environment. We again collect a set of demonstrations with the same strategy as in the hallway case. We see that our method finds a valid Lyapunov function and the policy rollouts are faithful to the demonstrations. The baseline, however, gets stuck in certain areas and is unable to reproduce the demonstrations. We explore the performance of our method in a manipulation task where the demonstrations are to take an object from the top of a shelf to a target position under the shelf. In all cases, the policy rollouts from our method and our baseline reach the goal. Our method reproduces the motion with and without the obstacle avoidance module. With collision avoidance, the motion from the baseline looks like the demonstrations, but solely due to the modulation. Without it, the baseline policy does not match demonstrations and collides with the shelf. We look at the effect of perturbations and find that the policy can robustly recover from them, since the policy is a state-dependent motion field and is guaranteed to reach the goal. We deploy the policy learned from experiment 2 on a physical robot. We see that it is able to perform the task without making contact with the shelf and performs the same as it did in simulation, achieving sim-to-real transfer reliably.